Okay, today we are going to cover sections 1, 2, 5, 4, and 5. 1, 2, 4, and 5 in chapter 2. The bell work was this Harry Potter logic puzzle that we will not spend too much time on. Sections 1, 2, 4, and 5 are going to cover conditional statements, inductive reasoning, deductive reasoning, and algebraic proofs or properties. We're going to go over the properties and then write some basic proofs. Okay. Vocab. Conditional statements. Logical statements that have a hypothesis and a conclusion. If-then form is a conditional statement written in the form of if P, then Q. The negation is the opposite of a statement. So if we say the statement is P, then the negation would be not P or written tilde P. Converse. The converse is the statement formed by exchanging the hypothesis and the conclusion of a conditional statement. The biconditional is a statement that contains the phrase if and only if. Equivalent statements are going to be two statements that are both true or both false. Inductive reasoning. Inductive reasoning starts with the letter I. I, me, my. I am a specific individual. If I can spell specific. I am a specific individual. So when we talk about inductive reasoning, this type of reasoning is going to start with a specific case and then go to a bigger picture, a generalization. I remember this by I, me, my. I am a specific individual, so I start with the specific and go big. A conjecture is simply an unproven statement. Conjectures are based upon observations. Counterexamples are specific cases that prove our conjectures false. Deductive reasoning, the other type of reasoning, is simply the reverse. It's the opposite of inductive reasoning. So if inductive reasoning is I, me, my, specific to general, deductive is general to specific. Deductive reasoning is often based upon facts, definitions, laws of logic. This is how we base our logical arguments, is often on deductive reasoning. Proof. A proof is an argument that uses deductive reasoning to show that a statement is true. Okay. Inductive reasoning is we are going to look at some specific cases and make a generalization. We need to find the sum of the first 20 odd numbers. The sum of the first odd number, or 1, is 1. The sum of the first 2, 1 and 3, would be 4. The first 3, 1, 3, and 5, is 9. And the first 4 is 1, 3, 5, 9, which is 16. Looking at this, you should be able to see the pattern that this is equal to 1 squared. The number of numbers and then squared. Oops. Got that too close. So, that would be 2 squared, 3 squared, 4 squared. So if we need to find the sum of the first 20 odd numbers, I would predict that that would be equal to 20 squared, which is 400. This is an example of using inductive reasoning to solve a problem. Now, let's work through some examples trying to determine the difference between inductive and deductive reasoning. Number 3 says, all men are mortal. Joe is a man, therefore Joe is mortal. Okay. Big picture to a specific person. So is that I or D? Well, I is when I'm talking about I, me, my, or a specific case. So that means 3 must be deductive. Number 4. Bachelors are unmarried men. Bill is unmarried, therefore Bill is a bachelor. Bachelors, big picture to a specific instance. So, deductive. Most universities and colleges in Utah ban alcohol. Most universities and colleges in the U.S. ban alcohol. So we would start with a specific state and move to a bigger, broader picture. This is an example of inductive reasoning. This marble from the bag is black. That marble from the bag is black. A third marble from the bag is black. Therefore, all of the marbles in the bag are black. So I started with specific cases, and then I went to the more generalized term. So this would be inductive. Okay, so let's look at counterexamples. A counterexample is just one example that is going to prove our statement false. Number 7 says that x squared is greater than x. We want to prove this false. So change colors. What if x is 1? Well, x squared is 1 squared is 1. What's the relationship between x, or 1, and 1? That would be equal. 1 is not greater than 1, so this x equals 1 is a counterexample. So the sum of two numbers, x plus y, is always greater than their difference. We want to prove this false. If x is positive and y is negative, let's try that. So 5 plus negative 2 would be 3. And then we have 5 minus negative 2 is 7. 3 is less than 7, so 3 is not greater than 7. So this, x is 5, y being negative 2, would be a counterexample. Let's move on to the algebraic properties of equality. Okay. The algebraic properties of equality are based upon the assumption that a, b, and c are numbers and a is equal to b. So, the addition property says that if a is equal to b, then when we add a to c, it should be the same as adding b to c. Then if we take c away, it should be the same on both sides. Again, for multiplication and division. And that is because A and B are supposed to be equal. If A and B are equal, then when we look at substitution, that means that A can be substituted for B in any equation. Can be substituted for B. The commutative property says that when we add A and B, it should be the same as adding B and A. And the same thing for multiplication. No matter the order, we should still get the same value. The associative property. If we have three values, A, B, and C, then no matter which ones we do first, we should still get the same value again. So if we multiply A and B, then times C, should be the same as B and C times A. Distributive property. If we multiply A times the sum of B and C, it should be the same as the product of AB plus the product of AC. We can do this where the sum is first as well. We should still get the same thing. Transitive property. So if we already know that A is equal to B, and then B is equal to C, then we can say that A is also equal to C. The reflexive property. When we see the word reflexive, we should see the word reflection. We should be able to make that connection. Reflection. They're really similar. We typically see our reflection in a mirror. Therefore, the reflexive property gives us the mirror image, or A is equal to A. Symmetric property says that if A is equal to B, then we should be able to switch it and say B is equal to A. Now, let's use these and build our way up to writing our own algebraic proof. We want to give a reason for each step. Okay, the very first step, the very first thing we always want to do is write given, because we will always be given the problem. Now, the next part. I need to know, how did we go from negative 4x plus 9 equals 21 to negative 4x equals 12? You should see that they subtracted 9 from both sides of the equal sign. So the reason would be subtraction. Okay? The next line says that x is equal to negative 3. How do we go from negative 4x equals 12 to x equals negative 3? They divided by 4. So the reason for that would be division. It's as simple as that. We just have to remember that the reason we are given on each line matches up to what happened between the line previous, okay? Look at number 10. The very first line will always be given. Here, we distributed the 4 to get 4 and 16. So, distribution. Next, they subtracted the 8 and moved it to the other side of the equal sign to get the negative 4. So that would be subtraction. To go from 4x plus 16 to 4x, they moved the 16 to the other side of the equal sign. They subtracted again. Now the very last thing they did to go from 4x to x is they divided by negative 4 on both sides. So division would be the final reason. Okay. Let's look at another one. Very first is always given. Now, we want to see how did they go from 1/3 x to x, negative 10 to negative 30, and then 9 to 27. They multiplied. Okay. Next, how did they go from x minus 30 to negative 30? They subtracted x from both sides. Last part, they divided by 26 on both sides to get negative 15 over 30. Now, it is very important that we show the difference between these two steps here. We cannot flip the x around to the other side without first solving and then flipping it with the symmetric property. Okay, so let's use this and write our own proof. Very first statement is going to be the problem. And the reason will always be given. And you have to write this. Every single time you're asked to write a 2-column proof, you have to give the problem that was given and tell us that the reason was because it was given. Now, to solve for x, we will begin by adding 11 to both sides. When we add the 11 to both sides, we will have 2x is equal to 32. And the reason was addition. Last thing we need to do to get x is divide by 2. And we would get x is 16. So the reason for getting x is 16 is division. So, we have just completed our first proof. There is some extra classwork on counterexamples on the back side of the notes paper, and these are the homework problems that accompany this part of the lecture. So, have fun, good luck.